Okay, so today we're going to start chapter 17. This is actually chapter 13 in the new book, chapter 17 in the old book. Okay, got the old numbers in my head. So all we're going to really talk about in this chapter is about lipids. So in the last chapter, we spent all about carbohydrates, then we're going to do lipids, then we're going to talk all about amino acids, and then nucleic acids. So we're covering our four big biomolecule groups. So a lipid is a compound isolated from body tissues that is more soluble in organic solvents than in water. And what this means is, if we think back to our solutions, this means that these fats tend to be non-polar, okay? Because if they're not dissolving in water, which is polar, but dissolving in something that is not polar, remember, one of the rules we talked about was like dissolves like. All right, so fortunately, your book has a really great image. Looks much better than the black and white that was on my slideshow, so I took a picture of the color image. And this is our organizational chart. So everything that we talk about is going to fall under the lipid category, but then we're going to have a group that's called fatty acids, and then a group steroids. And just like a family tree, there are going to be different types of fatty acids, different types of sphingolipids, and different types of glycolipids. Okay, so it's just like a family tree, and they're all going to be related, normally based on structural similarities is what we're going to see. But I really recommend this to help keep you organized. Okay, so always kind of come back and maybe make a flow chart with the information about what makes them different. That might help you study for the test. All right, so let's start off at the top. We're going to start with fatty acids. Okay, so what are fatty acids? Well, they are a carboxylic acid. So I drew this up here to remind us what carboxylic acid is. And that is a structural component of fats and oils. Okay, so it's kind of it's a functional group identifier. Typically, our fatty acids are going to contain an even number of carbon atoms, typically between 12 and 20 carbons long. They are unbranched, meaning they're straight chains, and they are going to be classified by the presence and the number of carbon-to-carbon double bonds. Okay, so remember, carbon-carbon double bonds are these right here. So we're going to have three different types of fatty acids. The first is a saturated fatty acid. This is a fatty acid that has no carbon-carbon double bonds, only carbon-carbon single bonds. Now, a mono unsaturated fatty acid is a fatty acid that has only one carbon-carbon double bond, and a polyunsaturated fatty acid is going to have two or more carbon-carbon double bonds. Okay, so given the structure, we could identify whether or not it is saturated, mono, or polysaturated. So if we're looking at this chart right here, these are the common fatty acids found in natural fats. So things we can buy. You'll see palm kernel oil, macadamia oil, cocoa butter, olive oil, canola, flaxseed, probably liver oil. Maybe those sound familiar to you. So looking at the structures, I see one double bond here. So that would be a mono unsaturated fat. And then if I look here, in the one that is below the gray box at canola oil, there is a 2 outside this parentheses, which means I have 2 double bonds. Just like before, it's going to distribute in. So this would be an example of a polyunsaturated fat. Okay. So remember, because it has CH2CH, what this really means is that there are 2 of everything in this parentheses. Okay, so that's how we make the distinctions between saturated, monounsaturated, and polyunsaturated. You do not need to memorize the names or anything on this chart. However, this chart may be helpful because sapling is going to ask you to draw some of these oils or fats, and I'm not asking you to memorize them. So having this chart may be helpful to get you started. All right, so essential fatty acids. These are fatty acids that we must obtain from our diet because it cannot be synthesized by the human body. Okay, so we have a lot of things that are essential in that same sense, but that's what it is to be an essential fatty acid. All right, so the next thing that we're going to talk about are our waxes. Excuse me. So if we go back up, we're going to talk a little bit about waxes. So waxes are esters. Okay, so if we think about the functional group for ester, it would look something like this. And they are formed from long-chain fatty acids and long-chain alcohol groups. Okay, so long-chain fatty acids, which we just talked about, and long-chain alcohol groups. So we have plant waxes, which are on the surface of leaves. If you ever touch the leaf on the top, you can tell it feels different than maybe the leaf on the bottom. Flowers, fruits, and these are things that protect the plant from dehydration, so from the loss of water, and also from the invasion by harmful microorganisms. Now, animals, on the other hand, will produce waxes that serve as protective coatings. So some examples are things that would protect the surface of feathers, skin, and hair pliable, also acting as a water repellent. So remember, wax, water repellent, which just reiterates the idea that these are non-polar and water is polar. Okay, so they do not mesh well. All right, so in sapling, it's going to ask you to do some things like writing the condensed structural formula for each fatty acid. So if we think about this, we have oleic acid. Let's see if it's on our table up here. It is. So this is the structural formula, and this is the condensed structural formula right there. So if I was on sapling, one of the things I would want to do is to write the condensed structural formula for oleic acid. And it's given right up here. So the next one is alpha linolenic and then palmitic acid. So we look up on our chart, we see that they're both right here. Okay? Did I get both of those right? Oh, alpha. And so what we want to do is on your in-class assignment, this is going to be in-class assignment. Today should be the 11th, I believe. And just make sure you put your name. And you're going to write out the condensed structures for this one, palmitic acid, alpha linolenic, and oleic. Okay? So after you do that, it's going to be the one in this column right here. So I'm going to leave that here for just a little bit so you can identify, or so you can copy that. Maybe zoom in a little bit. And then off to the side, let's identify whether these are saturated, monounsaturated, or polysaturated. So starting off with the first one, we see that there are no double bonds drawn in. So that would tell me that this is an example of a saturated fat because all the double bonds are going to be drawn in to explicitly show them when we have the condensed structural formula. So if we look at the abbreviated structural formula, there's no details in the second column that tell me if there's a double bond or not. I need the condensed structural formula to see those double bonds. So looking at the next one, I see that I have one double bond here at the very center. There's no parentheses around this group, which tells me I only have one. And this would be monounsaturated fat. And I look at the last one, I see that I have a double bond here, but there's a 3 on the outside of the parentheses, which means I actually have 3 of everything in that group, which includes the double bond. So that would make this a polyunsaturated fat. So I'm going to leave this up here for just a few more minutes to give y'all a chance to, you may not have had your paper out quite yet. You may not have been prepared to go as fast as that in-class showed up. Okay, so give you just a chance to write these answers down, and just make sure you write your name and put the date on it. And hopefully this will help you with the sapling homework as far as looking or writing in what they're looking for. Okay. All right, so now we're going to move on to talking about fats and oils. So if we think about our flow chart, we're still talking about fatty acids, but we're going to talk specifically about fats and oils. So fats and oils as a group or as a family are the most abundant lipids in nature. Okay, so that sounds like a really good thing to know, maybe test question material. They provide energy for living organisms, insulating body organs, and then transporting fat-soluble vitamins through the blood. So it's not just responsible for one thing, they are responsible for a lot of really important things. Energy, insulation for our organs, and then transporting vitamins that are fat-soluble through the blood. So they have to be soluble in fat, meaning they have to dissolve within fat and oil to be transported. So often, fats and oils as a collective are called triglycerides. So you've probably heard of triglycerides because of blood work and overall body health. But a triglyceride, as far as a definition, is an ester composed of 3 fatty acid units linked to glycerol and found in fats and oils. So what that looks like is here are my 3 fatty acids. They're my straight chains with my OH groups and my carbonyl. They're going to react with something that's called glycerol. So there's 3 carbons in a row, and each carbon has a OH group. There is a catalyst which just makes the reaction occur. And what forms is you take the glycerol, and they are going to link up with the fatty acids. Okay. Now the thing about the fatty acid chains right here is that they can be different, right? So we're just leaving the door open for what R could be. And then we're going to have the loss of water. Okay. So it doesn't really matter how you think about the water forming, but in this case I'm going to take the hydrogen on the left and the OH group that I didn't draw all the way in on all of them on the left. Okay, so these 3 things, or these 3 waters, are going to form, and what that means is, So I want y'all to look up at the board. When these go away, we have a new carbon-oxygen bond that forms. Okay, so I believe sapling homework is going to ask you to draw this, and this is kind of what it wants you to do. It's going to give you the glycerol, it's going to give you the fatty acids, and it wants you to remove the water, which is a hydrogen from one and the OH from the other, and then connect them. Okay, and this now is no longer glycerol or a fatty acid, but it's called a triglyceride. Okay, tri meaning 3. All right. So if all 3 of the fatty acids are the same, we call it a simple triglyceride. Except what you can't see, it says right here, is that this is very rare in nature, meaning most of the time our fatty acids are all unique. A typical triglyceride obtained from naturally occurring fats and oil contains 2 or 3 different fatty acid chains, thus we call it a mixed triglyceride. Okay, so a simple triglyceride, the fatty acids would all be the same. Identical. In a mixed triglyceride, fatty acids are unique. At least 2 are unique. Now, if the other one's more rare, this is more commonly seen. All right, so let's talk about something that we probably see and we've probably observed before. And that's that we have different types of fats at their phases are different at room temperature, right? So a triglyceride is called a fat if it is solid at 25 degrees Celsius. And liquid we call oil. So for example, right here, butter is an example of a fat that is solid at 25 degrees Celsius. Oils, so right here I have vegetable oil, canola oil, olive oil. These are examples of triglycerides that are oils because they are liquid at room temperature. Okay, so that's how we distinguish between fats and oils, is based on their phase at room temperature, which we say is 25 degrees Celsius. Now there are some interesting ones. At least I think coconut oil is an interesting one because I've bought coconut oil and it's completely solid, and then I've purchased some that's, when I bring it home, it's completely liquid. And I don't know if it's because I keep the temperature in my house a little bit warmer to save money on electricity. But coconut oil seems to be right there on that line of sometimes it's a liquid, sometimes it's a solid. In general, we tend to think of fats as animal sourced, and we tend to think of oils as plant sourced, meaning we get them from plant sources or we get them from animal sources. So that's another general rule of thumb as well. All right, so physical properties of fats and oils. Pure fats and oils are colorless, odorless, and tasteless. Now, there is a little bit of an exception because they can go rancid, and if they go rancid, spoil, then of course they smell. But if they are not rancid and they are pure, they are colorless, odorless, and tasteless. Now, another property is that oils and fats are lighter than water, and their densities are about 0.8 grams per cubic centimeters, and the density of water, remember, is about 1. Meaning that if I had a container and this was water down here, the oil I would expect would be on top. And they are poor conductors of heat and electricity, and of course, they are not polar. Hence why we see that these tend to be what's called give myself some more space. Oops. Miscible, meaning they do not mix. All right, so one of the labs that we did, if you remember, was we made soaps and we tested their soaping ability. So that reaction is called saponification, which sounds very strange, but it is the hydrolysis of fats and oils and the presence of a base, which tends to be sodium hydroxide, one of our strong bases, NaOH, to make soap. Okay, so Sapling's going to ask you to draw something very similar, and this is kind of what it's wanting you to draw, but we did a lab on this. In fact, I think, if I'm not mistaken, it's not, because I'm recording this on September 20, I don't even know what today is anymore, 28th? So I'm recording this on September 28th, and I think that we are doing this, not this coming Monday, but the following Monday. Yes, it's Saturday, thank you. Anderson's telling me it's Saturday, which is true. Very smart. All right, so membranes and membrane lipids. So we're just going to start this topic because it's fixing to get very confusing. Because when we start talking, we've talked about triglycerides. When we start talking about membranes and lipids, we are going to get into all of this other mess that's out here. And then steroids we'll save for last because it's kind of a good place to end. Okay? So let's scroll down and look at the membrane lipids. Okay, so all living cells, whether they're plant or animal, are surrounded by what's called a cell membrane. Plant and animal cells contain a nucleus that is also surrounded by a membrane that holds the genetic information. So it's really important to protect the genetic material, right? Because that's what is going to dictate the ability to pass on the genes. So we want to protect the genetic material. And membranes are a really great way of doing that. Now the cytoplasm, might be something you're familiar with, is everything that is located between the outer cell membrane and what we call the nuclear membrane, which this is where the genetic material lives. So that's the cytoplasm. And then the membranes of all cells have a fundamentally similar structure, meaning they share a lot of similarities, but they're different in slight ways. Membrane function varies tremendously depending upon different proteins and lipids present in the membrane. So there's small changes that make them very unique, but structurally they seem to have very similar features. So fortunately, I have a really great image from the textbook. The one I had was black and white. This one is colored, so it's great. So we see here this is cell wall. This is our cellulose, carbs coming back to show themselves. And then inside the cell wall, we have the cell membrane. So this is where we are when we're talking about our fatty acids right now. Then you have all kinds of different features. We're not going to worry about any of those. But then right here, we have the nucleus. And then what surrounds this is a membrane, which protects the nucleus from everything else. And so you'll see cytoplasm right here in green, in the very center, right here in the corner, is everything else in between the cell membrane and the nucleus. Now this is called an idealized plant cell because it shows every little thing that might be in the plant cell and it looks perfect, but that's not how it always is. So now let's look at the animal cell. So the animal cell, we have the outer cell membrane, which is here. And then we look for the cytoplasm. It's everything kind of in the tannish color that we see. We have the nucleolus, as well as the nucleus, okay? And that entire nucleus, similar to the plant, is surrounded by a nuclear membrane, okay? So we're going to see lipids and a lot of this stuff. And I'm sorry, this shouldn't have been fatty acids. I have a little bird chirping in my ear. This should be lipids. All right, so chemical reactions of fats and oils. So we see that lipids and cell membranes are highly polar, but they have a dual characteristics. So they show two different properties. The first is we have what's called a hydrophilic portion and then a hydrophobic portion. So anytime you have philic, we're thinking of loving, and hydro means water. So this is water loving. The other side is hydrophobic, water fearing. It does not have an affinity for water. And so lipids are going to have this dual characteristic, but it's not without purpose. It's with great purpose that they are dual natured. Okay. So when these fats and oils are allowed to float freely in water, polar lipids will spontaneously cluster together in any one of three arrangements: micelles, monolayers, and bilayers. Okay, so a micelle is an aggregation in which the nonpolar tail is directed towards the center of the structure and the polar head is directed outward. So it looks something like this. And micelles are what helps to clean our clothes. Okay, they help with soap, taking all the dirt off. The dirt, which wants to be here in the center because it is not polar. And then out here is the water. So the micelles pick up the dirt off your clothes and then move it out and leave your clothes clean. So that's kind of the micelles in action. The next kind is called a monolayer, and this is where you have a layer 1 molecule thick on the surface of the water. The polar head faces into the water and the non-polar tails stick up into the air. And I have an example of that here. Okay, so if we had, let's see, a test tube, and the test tube is full of water, you would see that the polar heads point down into the water and the non-polar tails point up. Now the next one is probably the most important to us, and that's the bilayer, because that is what produces the lipid bilayer that's important for our cell membrane. So when this does it, it says that a double layer of lipids arranged so that the non-polar tails are forced between an inner surface and outer surface consisting of hydrophilic heads. So I'm going to skip down a little bit. And you can see it kind of right here. But we're going to see a really great colored image when we start next time's lecture, because my image is going to look very bad compared to the one they're going to have, and it's going to have way more details, which is why it's good to kind of start with a simplistic one, because we're only focusing on the details that matter. Okay, so the inside is nonpolar, the outside is polar, and so what we see is water and water. Okay, so this is what cell membranes look like. Okay, so here in a test tube, it's just a really grainy image. It doesn't do a very good job. My drawings are not the best, but this is so grainy it's really hard to see. So I hope that this will help you. We should have spent probably about maybe 32 minutes in lecture. So I want you to take time to ask Dr. Morris or Dr. Spencer, whoever's with you, questions about the material, and that way you have someone there with you that can help you. We will finish chapter 13 on November 13th, and then hopefully there'll be time for questions.